Hi everyone, in this presentation I'm going to discuss analysis of triaxial test. And again, it's going to be from designer point of view, conceptual. Second part, we are going to discuss practical examples for triaxial test and what you can encounter during analysis and complications. So outline, we are going to discuss today unconfined compression strengths when you can assess only under insurance strengths. UU test, also you can assess under insurance strengths, and maybe sometimes people saying C5. Consolidated and drain test, you can assess both cohesion and friction effective and total. We're going to discuss a little bit about what difference between total and effective. CD test, consolidated drain, when you can assess only effective values, friction angle and cohesion. And multi-stage triaxial, which actually almost with respect to analysis results, you can get both. If like CU, like a multi-stage consolidated undrained, you can get like C5, C prime, C prime. If you're going to make multi-stage consolidated drain, so you can get only effective values, C prime, Phi prime. Okay. I just like to show you different equipment frames and what's the difference. The difference is very simple. So when you doing like your unconfined compression strengths in the equipment, and then actually when you're going to do UU test, CU test, CD test, it's actually the same frames. The difference between these two tests, the only difference is for UU, CU, CD, you can get some cylinder, like let's show you this one cylinder. So it's actually plastic glass inside your sample, and you can apply your confined pressure, which actually you cannot do for unconfined compression strength. Why? Because it's just you trim sample, put under piston and draw. So no confined pressure for unconfined compression strength. This is called unconfined compression strength. Okay. So I just would like to show you different equipment. You can see equipment which is right corner, low corner. It's like produced by manufacturer, and this equipment was produced by people themselves. So they just bought manometers, regulators, cells, and connected by themselves. So it's cheap. They save the money. I just would like to show it's like just example, and this one me when I was young and handsome. Joke, guys. But yeah, it was around 25 years ago, so much younger. Anyway, let's start. So we're going to talk first for unconfined compression test, which you can get CU or SU, by the way, the same value, but sometimes people are using different notations, doesn't matter. So you have only one stage, sure. So, and the only thing, you don't apply any confined pressure. So you take sample, trim it, place it in frame and break it like concrete cylinders, and you're getting some maximum axial stress. By the way, guys, it's very funny. Sometimes people normal stress, axial stress, and it's exactly the same. Doesn't matter. So because people like if it's cylinder, definitely it's normal. Why? Because it's 90 degrees. Why it's like vertical, like axial? Definitely axial. Why? Because it's according to y-axis. So I just don't know. People like love it to call it differently. At the end of the day, it's the same. Okay. And this one, unconfined compression strength, 72 kilopascal for this specific case. How to get under insurance strength, which you're going to use for your design purposes? Pretty straightforward. It's half of your unconfined compression strength. And why is that? More circles. Guys, it's pretty straightforward. So you take your 72 kilopascal, put on a horizontal line, make circle with diameter equal 72 divided by 2, so it's 36. And that's it, guys. It's pretty straightforward. 36 kilopascal it's your CU or SU, doesn't matter how you're going to call it. Okay, straightforward. And you're using the same equipment, the same thing. UU test, unconsolidated, undrained. So for this test, you have 3 stages. Oh, only 1 stage as well. But you have to apply confined pressure. But guys, just remember, no saturations. Just remember it. ASTM standard doesn't say, or like standards, you don't make any saturation. It's a very important point. We're going to discuss it later. So based on theory, like doesn't matter what, it's like all textbooks saying, you doesn't matter what confined pressure you apply, you're getting for the same material, the same circles. Guys, it's only correct for fully saturated clays or materials, and it should be absolutely identical with respect to dry density. So it should be identical samples. Now, guys, in practice, it's absolutely wrong, which no one in the university somehow don't tell about that. And I was so happy when I found this standard, like Federal Highway Authorities, like IF 02032, and it was a report date. It's like textbooks, very good, like 2002. So these guys, they did know very well. You don't get like this one, like the same diameter. What you get, they apply higher confined pressure. You generally get higher undrained shear strength. And the reason why, very simple. Because according to STM, you don't saturate it. So when you trim, when you put inside cell, you put your rubber sleeve, you put your plates and the pistons, you have every time air between all these areas. And during trimming, you already put air inside your sample. So it's not fully saturated. When it's not fully saturated, you every time apply it higher. I don't speak about you have different densities. It means the denser material getting higher, but I even don't talk about that. But generally, you don't get the same diameter. Just keep it in mind. And don't blame lab, or they did bad test just because they didn't get whatever in the book. In the book, it's just theory. In practice, it's what you can get. Okay? Okay, consolidated drain, undrained, consolidated, undrained test. So in this case, appear all 3 stages: saturation, consolidation, and shear. And what I just would like to tell you guys, just remember forever. When people and engineers say, oh, it's universities measure minor stresses, it's very nice, I love it, like, but it doesn't exist real world. What you're dealing during the tests, you're dealing with cell pressure, with back pressure, force, and deformation. Rest of stuff is just pure calculations. Even like I just would like to tell you, and I'd show you, because some labs I just was surprised once, they forgot to put like filter paper and they could not saturate sample during like more than 3 weeks because it was the wrong approach. To make a long story short, consolidated undrained. Why it's undrained? Because the valve here is going to be closed during the shear stage. Okay, just keep it in mind. And I just would like to tell you one thing: you have to design your triaxial test, CU or CD. What does it mean? From 2 sides, engineer side and lab side. From rule of thumb, just keep in mind what many engineers saying, oh, please apply stresses according to STM. ASTM, British standard, Chinese standard, Japanese standard, doesn't matter what standard, doesn't tell you what stresses should be applied during consolidation stage. It's up to design engineer. Rule of thumb, very simple. If you have overburden stress, effective, so for sample B, you apply overburden stress. For sample A, you apply half of your overburden stress, and for sample C, doubled overburden stress. The reason why, guys, very simple. When I see some engineers saying, oh, let's say 100 kilopascal for sample A, 120 for sample B, 140 for sample C, guys, in 99% it doesn't work. Why? Because sample is not homogeneous. To get proper Mohs circles, you have to double, make it by bigger distances between all three circles, and then you get very nice. If you got very small gaps, you're going to get total mess. For lab, I just give small tip, guys. Rule of thumb: the low dry density, the low confined pressure. How you assess it? Very simple. You have trim material during preparation, trimming samples. You assessing anyway moisture content originally. Assess roughly dry density. The low dry density, the low confined pressure. The high dry density, the high confined pressure. Just tips for you guys. Okay, so let's saturation. So what you operate with cell pressure, back pressure, and volume during saturation. Then during shear stage, you have pore pressure, and actually you are looking for excessive pore pressure. Your cell pressure is constant, and your force or deviator stress changing. And by the way, keep in mind, I'm not going to discuss in this presentation regarding all corrections. Correction for area, correction for rubber sleeve, correction for filter paper. All these corrections will influence on your deviator stress. In university, even no one talk about that, or talk just very short. When you do all exercising, people just doing, oh, your deviator stress, your major, minor, and etc. Guys, you don't have it everything. You have whatever I just wrote down here. And then what you have, consolidation. It's cell pressure, back pressure. Your excessive pore pressure, it's your pore pressure at the moment failure, and initial your pressure, it's what your excessive pore pressure. Your major principle, oh, we finally get it. It's sigma 3 plus deviator stress. And your effective measure in minor principle is just your sigma 3 and sigma 1 minus excessive pore pressure. It's what this one stuff. Okay? And select your strain of rate. Why? Because if you didn't pick up, guys, again, it's not design engineer, it's labs. If your pace of the shearing, pushing piston very high, your excessive pore pressure could be jumped too high. Okay? All equations in here, not including changing area changing, rubber sleeve resistance, and filter pipe resistance. You can pick up different criteria for failure. So STM provides 3. I do know additional one based on maximum pore pressure. If your principal stress is different, deviator stress, drop 20% during test, stop the test. And the test should be stopped because it's nothing, no reason for continue generally. When 5% of additional axial strain occur after peak in principal stresses, you can also complete your test. During analysis, and we are going to talk about that in part 2, you have to look dry density, shear profile, B value during saturation, and all information provided generally in the report, and curve shapes. Rule of thumb, normally consolidated soils fail as a bulge shape. Over-consolidated soils failure as a shear plane. So you can shear plane here. Okay? Now pay attention. In reality, very often you will get combination of bulging and shear planes shapes of deformation during the shear. Okay, I just would like to talk about criteria. So And this very important because depends on criteria you're going to pick up during your analysis. You can get different friction angle and cohesion. Okay, for example, let's assume you pick up deviator stress, maximum deviator stress. Then you have to pick up maximum deviator stress, make projection on the same curve of your excessive flow pressure, and get your excessive flow pressure. If you picked up, for example, maximum stress pressure, you are going to get absolutely different maximum deviator stress or deviator stress, and excessive flow pressure is going to be used for calculation. By the way, just take a look. In this case, you have negative pore pressure. That means when you calculate your effective sigma 1 is going to be sigma 3 prime minus u. This one is u. Okay, so it's going to be plus. Just keep it in mind. It's very important. Okay, so let's analyze. Let's take one example of triaxial, just one, because in the second part I'm going to give you different scenario in different kind of options. Okay, let's assume in this specific case we take maximum stress ratio for calculation of our deviator stress and excessive flow pressure. Let's for sample A. Okay, pick up, you see this point, pick up this point because we took it as a criteria. Make projection on the same curves sample A and projection to find what excessive flow pressure and deviator stress. And by the way, you have to write down somewhere these values to build up your Mohr circles. The same procedure you're doing for sample B. You see green one. Again, you take these values in your summary table. And for sample C. And you write down all these 6 values. Deviator stress, 3 deviator stresses, and 3 pore pressures. And now let's construct Mohr circles. Next slide. Okay, so what I did, I took all values from previous slide, okay, and by the way, sample column, I just call, you see, you can see columns 3, 4, 5, 6. So it's taken from previous slide and or from results, because these parameters consolidation, it could not it was maybe taken from previous slide, maybe, or I don't remember. So it's everything from the test results you're taking. And the lab should provide it. And again, I just showed you it's from previous slide. Sigma 3 is actually from consolidation. And what does mean consolidation? It's cell pressure minus back pressure. Forget about major minor. Doesn't exist in the lab. Okay. Then all columns 7, 8, 9 is just pure math. Column 7, 6 plus 4, 8, 6 minus 5, 9, 7 minus 5. And this one, it's whatever I showed you in previous this one. So sigma, again, sorry, sigma 1, it's sigma 3 plus deviator, and effective sigma 1, it's sigma 1 total minus u. And all these columns, just I will explain exactly how to calculate. So you take first sample A, sigma 3, you take second point 630, and you have actually Mohr circle with center of circle, it's 630 plus 197 divided by 2, with diameter 630 plus 197 divided by 2. Okay? You repeat the same procedure for specimen B and specimen C. And then you build your envelope to assess your friction angle and cohesion. To draw circles in effective stresses, you just subtract your excessive pore pressure, and you build, like initially you build based on sigma 3, sigma 1, and the second one you have to build based on sigma 3 prime and sigma, and you're getting two different friction angles and two different cohesion values. That's it. Pretty straightforward, guys. It's so simple. Nothing else. Now, there is another technique, stress path. So what you're doing here, you draw like curves based on these results, and this what you're doing, you sigma 1 prime, and now you're dealing with major, minor, doesn't matter what. So you already forget about cell pressure, back pressure, and it's already math again. Sigma 1 plus sigma 3 divided by 2, and sigma 1 minus sigma 3 divided by 2, okay? And you building these curves based on these parameters. For each point, you have sigma 1, sigma 3, sigma 1 prime, sigma 3 prime, okay? And this called MAT. Why? Because I'm just show you example. So you get B value, you calculate angle alpha and A, and you calculate friction. Now, just keep in mind, before in previous slides, we just literally take deviator stress and strain, and you just literally from geometry by you can just measure your angle, friction angle, and cohesion. When you're doing in this technique stress path, you're already doing math, so you cannot literally take and measure angle. It's not going to be friction angle, and the ordinate is not going to be cohesion. Okay, so you need to make it calculations. And by the way, this one is like, I don't know, European, this one American sine in power -1, or European arc sine. I don't know. I just showed different notations, how like equations people are using. And just keep in mind, when you do stress path techniques, you calculate effective values only, period. Now, Cambridge techniques, you say, what is the same? No, it's not the same. So you can see in previous one, it was sigma 1 prime plus sigma 3 divided by 2. Here we have kind of sigma 1 if you have different sigma 2 and sigma 3, but in our case in triaxial, sigma 2 and sigma 3 equal. So you're doing different axes, and the same procedure, the same B, you're getting again the same angle and the ordinates, but guys, it's different equations. Just keep in mind, it took me a while just realize people doing different techniques and getting different equations, and it took me maybe several months to figure out different techniques, okay? And again, it's only effective. Now, consolidated drain tests, it's exactly the same approach, the same more circles, the same sigma, you getting the same values from cell pressure, back pressure, pore pressure, everything is the same. The only thing, the same techniques, but the valve here is open. So you don't have excessive pore pressure. As a result, you can get total friction angle and total cohesion. Only effective. Remember that for CD tests. And by the way, most of professors at universities doing all the exercises and let's put this way, all researches on CD tests, because it's much longer, takes much longer than CU tests. Just keep in mind. And multi-stage. What does it mean multi-stage? By the way, I just took it from head because there is the best ever book for all lab test results, head. There is different versions, but I have from 1980. It's the best book ever. So the main reason for this one, multi-stage, when you don't have enough material or your sample too big, so you can extract only one specimen, so you do multi-staging, okay? Or it's you cannot don't do with source which has low sensitivity. Okay, it's essential very how you're going to pick up failure. I'm going to talk a little bit, but it's very complicated. I would prefer not to carry out multi-stage because lab guys should be so experienced and knowledgeable to carry out properly this test, because you need to know when to stop your stage 1, stage 2. So what's happening, let me just explain you principal stresses whatsoever. It's just based on my experience, multi-stage better to analyze using principal stress ratio, guys. Just keep it in mind, okay, if you're going to bump multi-stage. And excessive deformation should be avoided. But again, it's actually not for you, not for designers, it's for lab. Again, should be very experienced guys who is doing this test. And so what's happening, I'm explaining what's happening. You take your you have only one specimen, okay? You start sharing. In some point, before it's failed, you have to stop, unload your loads, go back, take it forth, and initially you apply sigma 3, 1. That means, let's say 50 kilopascal. When you unload, you need to apply another stress, sigma 3, 2, for example, 100 kilopascal, and again, start sharing. Again, to stop somewhere, you see it stopped, stopped, stopped. So this one kind of, and you have to pick up these values. Generally for the third, when you have sigma 3.3, it's let's say 200 kilopascal, for example, you already can share to the end. You don't worry about that maximum strain, or like it could be to 15%. But again, main point here, how you're going to pick up your criteria to stop specific stage, because you have only one specimen. If you share properly, for example, in the first stage, you make like that, you're done. So whatever you can get, stage B and C, you can get only residual strength, C and phi, not peak. In this one, you guys, you have to take into account, but it's not even you, it's lab guys. So I would suggest you not to carry out multi-stage, because you need to make sure lab guys so good. So this one very good test, you see. So it's what I told you. They started, then shear, and some point when start already, yes, they shear a little bit, they start unloading. The next one, so you never ever get, you see, it's reach something, stopped, reach something, stop, and then you already share it. So it's if you don't have another choice, use it, but make sure lab guys experience and do not understand what they do. And thank you very much for your patience, and and I would like to see you guys next time, next my presentation. Take care.